Thanks everyone for joining today. Just to look ahead at what we're going to be talking about, we're going to focus on derivatives. There are all sorts of complex financial instruments. Today we're going to focus on derivatives, so we'll take a quick look at what sorts of derivatives we'll be talking about, what sorts of derivatives there are. And then we'll have a brief introduction to Neo4j, and we'll talk about why Neo4j is a good fit for this sort of a use case. We are going to be looking at a demo and doing some live queries. So I'm going to take a few minutes to talk about the Neo4j property graph and the graph data model, and do a quick introduction to Cypher, just so that when people see some of the queries we're writing later, hopefully they make a bit more sense. Then we'll dive into the demo, take a look at a few different scenarios, and as Angelica said, we'll wrap up with a bit of Q&A. So first, what are derivatives? So the official definition, or the one that I found here, is a financial instrument whose value is based on or derived from another security, such as stocks, bonds, and currencies. And they can also be seen as contracts between two parties. The derivatives value then normally depends on a risk factor, such as a credit event, an interest rate change, bond prices, currency changes, even sometimes weather data. So there's all sorts of derivatives, stock options, things like that. Mortgage-backed securities, which we'll be looking at later, are some of the ones that people are familiar with. It can get to be a bit of alphabet soup when you look at a list of different types of derivatives. So here's a few. We've got credit default swaps, CDSs. There's futures, put options, call options, swaps. There are over-the-counter traded derivatives, as well as exchange-traded derivatives. So it's a world unto itself, and there are plenty of people, maybe even on the call, who specialize in this and do this as part of their everyday jobs. It's also a very heavily regulated area. So financial services in general tend to be quite heavily regulated, but especially following the financial crisis of 2007-2008, which many people would say was brought on by some very complex and opaque, arcane derivatives. Since then, the regulatory landscape has really increased, and so there's a few regulations that we've listed here, just some of the many that would affect people who either sell or buy derivatives, including BCBS 239 and understanding how you aggregate risk and calculate and report risk. EMIR, Dodd-Frank, MiFID II, all of these have an impact on the derivatives markets. Today, we're really going to focus on mortgage-backed securities, and then what we'll call collateralized mortgage obligations. So the idea of a kind of a CDO squared, where you have packages of MBSs that are rolled up and then sold on as their own entity. So to drill into mortgage-backed securities a little bit, basically, if you're a financial organization that has a bunch of mortgages, maybe you want to get them off your books. There's a number of reasons you might want to do that. Maybe you want to change your risk profile. You want to get rid of some riskier loans, or you want to change your balance sheet so that you've got more cash to do more lending. For whatever reason, you decide you want to package up a number of mortgages and sell them as mortgage-backed securities. So you group them together into different tranches, and those tranches can then be sold on to investors, and they're graded according to the risk level and the quality of the loans that are packaged up in those tranches. So here we've got green representing good loans, low risk profile, going down to the red mortgages, which would be more risky, right? And there's a number of different reasons people might buy different grades of mortgage-backed securities. So at the top, obviously the low risk tranches. If you're quite risk averse, You might go for one of those sorts of MBSs. The expected yield would be lower on those because the risk is lower, but you have less likelihood of having to deal with losing your principal and dealing with defaults. Whereas at the lower end, the much riskier tranches, when there's a loss on any of the mortgages, those are the tranches that get hit first. The risk is much higher, so the risk of default would be higher, and the recovery rate on those loans might be lower. But because of that increased risk, you can expect a higher yield. So if you're not very risk averse, you might want to invest in riskier tranches with the expectation of higher yield because you can tolerate the extra risk. And then, as I said earlier, there's the idea of then being able to package up some of those tranches together into another tier of securities, right? So here we'll call them collateralized mortgage obligations. Basically, it's a collection of individual tranches that have been packaged into MBSs. Those are packaged together, which gives it a new risk profile. And kind of blends together some of the riskier loans with less risky loans to give you a new risk profile and a different set of options for how you can invest. So now we'll talk a little bit about Neo4j and why Neo4j is such a great fit for modeling and working with this type of data. So Neo4j is a graph database. It's the #1 database for connected data. And I think hopefully you've already gotten a sense of how connected the data is that goes into mortgage-backed securities, how complex it is and how highly connected that can be. So a graph database like Neo4j is a really natural fit for working with that kind of data. Neo4j is an enterprise-grade native graph database. So it's designed for performance and designed for enterprise use. So if you're a large organization that has many mortgages, lots of customers, lots of people that may be investing in these sorts of products, and you really need to be able to provide information to those people in real time, manage your risk in real time, deal with regulatory requirements in real time, then Neo4j is exactly the kind of database you would need. And the idea being that because the data is so highly connected, you can really use that to drive competitive advantage and real innovation in your organization, right? The sorts of data you might be using to combine together, even the data that we'll look at later, may come from all different parts of your organization and may be stored in different data silos already. So you might have customer data that you need to combine with product data. You might have market data coming in from third parties about the people in the organizations that you're loaning money to or that are investing with you. You need to combine that with data that goes into your balance sheet. So being able to combine all that together in real time and query it in real time at a very large scale really gives a lot of organizations who use Neo4j a distinct competitive advantage over other people who don't use this sort of technology. And you can see the reason why that would be. So traditional databases, relational databases, are oriented as tables, columns and rows. It's really good for storing ledger information or information as though it were a file in a filing cabinet. Being able to link all that information together can be really difficult, both technically and difficult to understand how it works. Whereas Neo4j stores data in a very connected fashion, which makes it easy to work with and means it can scale. You can trace connections and manage connections across large data sets very quickly and very easily. And what that allows you to do is really leverage your data so it no longer becomes discrete events, discrete bits of data. It really allows you to kind of move up the data value chain so that you can generate real insight and gain real wisdom from your data, being able to leverage the connections in your data and the context that brings you in real time. So just to talk a little bit before we get to the live demo about what a property graph looks like. So here we have a number of nodes. This is what makes up the Neo4j property model, so nodes and relationships. Nodes are the circles in this picture. They represent objects in the graph, so they're usually nouns in business language. And they can all be labeled, which is just a tag that you give the node so you know what you're working with. So here we have 2 person nodes and we have 1 car node. Each of those nodes can have properties associated with them. Properties are just key value pairs. So the person on the left, we know their name is Dan. We know Dan was born on May 29th, 1970, and we know that his Twitter handle is @Dan. On the right, we have a person named Anne, who was born December 5th, 1975. We don't know Anne's Twitter account, or maybe she doesn't have a Twitter account, and that's fine. So unlike a relational database where every row has the same number of columns and you need to fill them with null values if you don't have the data, in Neo4j, out of the box, it's schemaless. So it's okay to have different types of data associated with nodes that have the same label. So we also have relationships. Relationships are stored in the database between 2 nodes. Each relationship, when it's stored, has a direction. And sometimes that direction is important and sometimes it isn't. So for example, we can see Dan lives with Anne. In this case, the direction of the relationship isn't so important because if Dan lives with Anne, it wouldn't really be logically possible for Anne not to live with Dan. However, we do see that Dan loves Anne, and it would be entirely possible for poor Dan if Anne didn't love him back, right? It would be very sad, but quite possible. So in this case, luckily, they love each other, but here it's much more important to be able to understand the direction of that relationship. Relationships can also have properties associated with them. So we can see that Dan drives the car, and he has since January 10th, 2011, and Anne owns that car. We can see that it's a Volvo model V70. So each of those properties can be added to queries, when you're writing your queries in Cypher, and they can also be returned as data values. So those few simple parts really make up the entire graph data model and give it the power that we'll be able to see during the demo. We'll also be looking at some Cypher, and Cypher is the query language that Neo4j has written for working with graphs. It works somewhat like SQL, so if you're familiar with SQL for relational databases, some of it may look familiar. Here we have match, which is sort of like a SQL select statement. We're looking for a particular node. In the parentheses, we see it's kind of shaped like a node. In parentheses, we're looking for a person, and with the colon before the person indicates the label of the node that we're looking for. And then in the curly braces, we see the property of the node that we're looking for. So we're looking for a person node with the name of Dan. Then in the square braces, we see married to, and the colon married to indicates the label of the relationship we're looking for. And you can see that we've drawn the direction of the relationship. So the dash and the greater than sign show that we're looking for Dan being married to someone else. And then in the second set of parentheses, we see the word spouse. Basically what that tells Cypher to do, Neo4j to do, is to match whoever it is that Dan is married to and return that information in a variable called spouse so that we can work with that data afterwards. Okay, so now we'll take a look at the demo. We're going to be looking at 2 different interfaces. So first, we're going to use what's called the Neo4j browser. This is a tool that ships with every installation of Neo4j. It is very much geared towards developers, which is why we're going to be using it for part of this demo, because we're actually going to be writing queries and creating entities in the database. It's not as friendly for end users. It's not as good for visualization. So when we want to actually explore the graph, we're going to switch to another interface, which is called Neo4j Bloom, which is much more geared towards end users, much more user-friendly. You don't need to know Cypher. to be able to use it, and it just handles large visualizations much better. So first, to give you a sense of how we've set up the data in the database, we'll take a look at the metagraph here. So this describes how all of the nodes and relationships have been set up in the database. So starting on the right, we see that we have customers in the database, and customers can be related to each other, so they can cohabitate, maybe they're roommates or friends. They can be each other's spouse, or they can be family members, right? So maybe they're a parent and a child, or two siblings, something like this. Customers can be the borrower for a mortgage. And then associated with mortgages, we have a mortgage can have a product, and a product is just a type of mortgage, something that's being offered as a standard mortgage by the organization in this scenario. We also have some events, so we can represent late payments, and that will factor into some of the queries and risk calculations that we get to later on. In our database, mortgages are for a sale, and the reason I modeled it this way was because in real life, you could have remortgages, you could have mortgages for a number of different scenarios, but in this case, we're always talking about the purchase of a residential home. That sale is of a particular property, and then we have some address information for that property. So a property has a postcode. That postcode is located in a district. That district is located in a city. And we don't really use that geographical information too much in this scenario. All of the homes that we'll be looking at are from the Greater London area. But in real life, that geographic information could be really important as you start factoring in different elements into your risk formulas. So perhaps you want to package up mortgages into a tranche from different cities so that you're not exposed to significant market changes in one particular area. Perhaps the default rate in particular cities or particular districts is higher or lower. Perhaps there's a greater risk of flood or fire or something like this. So in real life, having that geographic information related to each of your mortgages is also quite useful. And then later, we'll start factoring in some additional node types. Mortgages will be put into tranches. Those tranches will be put into CMOs. Okay, and just to give you a sense of how big the graph is, here's all the different counts of the different node types, the different labels that we have. So in the system, we have just about 3,500 mortgages that we'll be working with, 5,000 customers. The different properties that we're looking at, there's, again, almost 3,500 of them, one for each mortgage. Those are spread across 3,360 postcodes, a handful of different cities and different districts. And then there's 21 products that are in the system, and we'll take a look at some of those and how they factor into our tranches and the types of mortgages that we have. Okay, so we'll start in Bloom. The last interface we saw was really driven by a window in which you typed your queries and got your results back. Bloom doesn't really have that same concept. It's all driven by the search bar that you see in the upper left. On the right-hand side of the screen, you can see a bunch of different colored lozenges. Each one of those represents the different node types, the different labels that we have in the database. So you can see we have our mortgages, our customers, our properties, our sales, just like we looked at in the metagraph previously. So if we start by looking at cities, we can take a look at some of the different geographic information we have. You can see there's London. There's also some smaller areas that sit around there. There's Sutton, there's Bromley, there's Romford, there's Ilford. So anyone from the London area, these might look familiar. We can then expand some of these. So if we look at London, we can see within London, there's a number of different areas. So there's the city of Westminster, there's Islington, there's Barnet, where I live. And then from there, we can drill down. We can see that there's quite a few separate postcodes in Barnet that represent the different areas where houses have been bought. And then from there, of course, we can drill into them and start getting a sense for the different properties that exist in those postcodes, right? So here we have Needham Terrace. I wonder if that's where our friend from Developer Relations, Mark Needham, lives. And you can see if I double click on that, we can get some of the detail here for this particular property. So we can get its full address. We have longitude and latitude, which might be interesting if we wanted to map some of the information we have here. We have a type. So T in this data set stands for terraced. So this is a terraced house. We also have semi-detached, detached, flats and maisonettes, all sorts of things. This data actually came from some open data in the UK. So the land registry is published in the UK, and it's really easy to see all of the purchases that have taken place of properties in the UK and the total price and when and where. So that's where I sourced this particular data set from. If we clear this out, then we can take a look at some of the products instead in a bit more detail and drill into some of the different mortgage types that we have in the database. You can see we have 21 products that are in the system. They're really broken down into a few different groups. We have some platinum products, and these would be for top tier customers of this bank. Maybe if you do a lot of banking with them, maybe you have a few different mortgages, or you have a credit card from them, you have a high salary and you deposit that to your bank. Whatever their criteria would be, some banks do offer premium mortgages with lower rates or different terms for premium members. Then we have a whole bunch of standard mortgages in 2, 3, and 5 year terms. And each of those is with a different LTV, a different loan to value ratio. So the one that I'm looking at here is a 5-year fixed standard. It's 80% LTV is the max loan to value ratio. And so the duration would be 60 months. We haven't done anything really fancy in this particular scenario with variable rates or when you reach the end of the duration for your particular interest rate, what that goes to. But of course, in real life, that sort of complexity would need to be folded into this system as well, right? So that when the 5 years is over, unless you remortgaged, you would probably fail over to a variable rate, something like that. And then, in addition to all of those, we do also have one of these in here somewhere is represents subprime. So it's probably best if I just search for it. So subprime. These are bespoke terms. So if you have a particularly bad credit rating, but the bank was interested still in working with you, they may offer you specific terms where your interest rate is adjusted according to the level of risk the bank perceives. So that's how I generated this data. All of the loans that are associated with the subprime product are there because the people who took out that loan had particularly low credit ratings, and therefore we could adjust the interest rate accordingly. So we can take a look at some of those. In fact, we can take a look at all of them. So it makes a nice picture. And perhaps you can see why we call this tool Bloom. As you can see, each one of those products has a number of mortgages that are associated with it, and then we can drill down into any one of those particular mortgages and get the specifics. So here we have a particular mortgage. This mortgage has an interest rate of 255, loan to value ratio of 80%. The principal on the loan is $240,000. The monthly payment calculated for that would be $95454, which would make the total value of the loan to this bank when all of the interest and principal are repaid $343,634. Then we have some other information. We have an overall risk calculation, which is a very simplistic formula I applied, which is based primarily on both credit risk as well as the salary of the people who took out the mortgage and how that compares to the total value of the loan. So people who have a low salary and a high loan and a high monthly payment are higher risk than someone who makes a lot of money and has a low valued loan. And then we can also see we have two individuals here who are associated with this loan. We have Farrell and we have Mateo, and they're related as family. So all of these things could factor into a real life risk calculation. Single borrowers may be perceived as higher risk than joint borrowers. People who are just cohabitating or as roommates may be considered a different risk than someone who's married, what have you, however your organization calculates that sort of risk. Okay, so now that we can see we have all these different types of mortgages and some of the values that are associated with each of those, we can take a look at how we might group them together into tranches and start creating some of our MBSs. So I've got some queries that I've already created. First, we're going to create a tranche with all of our platinum mortgages, right? So as this bank, we have high confidence in our platinum members. We know from historical data that these customers have a very low rate of default. We consider them very low risk. So therefore, we're going to package all of the platinum products up into a tranche. So what we do with this query, it looks quite long, but really it's just running a bunch of calculations so that we can create our tranche. We take to put into the tranche as different risk indicators. We're doing something very basic. So we're taking the average overall risk of all of the mortgages that we're putting into the tranche. We're then storing also the median risk and the maximum risk. So this will give us some indicators so that we could tell our investors the risk profile. In real life, there's a number of other calculations that you probably would want to put in there, but they're quite complicated to do in a demo scenario. So we'll leave that up to your imagination. We then also calculate the total principal for all of the loans that are going into the tranche, and then the total value of all of those loans once they're prepaid, when their terms come to an end. And the expected yield is basically just a calculation for the total value of all of the loans divided by the total principal. So this is the overall percentage of interest that would be paid out on this tranche over time. So this one we're going to call the platinum tranche, and we're going to link it with all of the mortgages that are in the platinum product. Okay. So you can see we've added one node, we've created one label, 544 relationships to that node, which means there's 544 mortgages that have been linked to this tranche. And you'll see, it's responded quite quickly, even though this is just running as Neo4j desktop on my laptop. So we're going to create several more of these now. We've got a AAA tranche, which would be, again, quite a senior level of investment and low risk. What we're doing here is taking only mortgages that are not already in a tranche. So we won't include any of the mortgages that have gone into the platinum tranche. We're only taking mortgages where the overall risk rating that was applied is less than 4%. We're taking only mortgages that have not had late payments. So any mortgage that's had a late payment would not be eligible for inclusion in the AAA tranche. And we're making sure that none of the customers associated with those mortgages have a credit score of less than 650. So you can see already how we're starting to leverage the different relationships that are in the graph and the different values that we can get from those relationships and those related entities. And then it's the same basic idea. We perform the same calculations, we create a new tranche, and we link all of the mortgages to that tranche. So in this case, it's quite a big one. Again, one new node was created. 1,280 mortgages have been associated with the AAA. And we'll do the same with a number of others. The AA is overall risk less than 10%. Again, no late payments, and this time people with a credit score of 600 or over. 336 of those have gone into AAA. AA, sorry. Triple B, in this case, we're looking for overall risk less than 20%. Again, credit score of 600, but we're at this point no longer interested in whether or not there are any late payments. So that's a pretty small one, only 94. Double B is, again, a higher level of risk. And again, we're not interested in late payments, and at this point, we're also not interested in the credit rating. And triple B would really probably be, in most real-life scenarios, the lowest level that you would actually offer for sale or investment. When we get down to the single B, that would normally, I think, or at least quite often, be something that the bank would then buy back or keep those mortgages for themselves to demonstrate, goodwill, and probably they would have a hard time selling them anyway. So that's the double B, and here's the B, is just everything else, all the mortgages that we have in the system that are not already in a tranche. There's 252 of those. So to go back to Bloom, we can take a look at some of those tranches then that we've created and get a sense for how they look. So here's our 6. If we take a look at the platinum tranche, we can see the expected yield is 27%. This is the total principal, so 214 million. And then if we take a look at, we'll say the double B, as we were saying, that's probably the last one that we would actually expect to be able to sell or present to investors. And this one, the expected yield is 35%, right? So the overall risk is higher. The average risk, the median risk, and the max risk are all higher than we saw in the platinum tranche. But then again, the expected yield is also higher, right? So that may be attractive to a certain class of investors. And then if we take a look, we can see these are all the mortgages that have gone into that particular tranche. Right? So just as we had before, we can still traverse the relationships between any of these particular mortgages. So we can see this mortgage, it has a 70% LTV, 505,000 is the overall loan value. We can see that it was for this particular house. Again, we can then trace the location of that house up through its postcode, its district, and so on. So we have all the same relationships. We just created a new container for them called tranche. And then we can do basically the same thing to wrap up tranches, into a new product. So if we wanted to create, as I said, we'll call them a CMO, a AAA CMO, by combining together the platinum tranche with the AA tranche. So a way of blending together a really good risk profile with still a pretty good one, but not as great, right? So platinum plus AAA, AA becomes something akin to a AAA, and that way we've mixed up a little bit our risk profile. Okay. And we can do the same thing to make a AA. In this case, we're going to combine the AAA tranche that we made before with the BBB tranche. So a strong AAA tranche with a low risk profile with the BBB, which is still pretty good, but has a bit more risk available to it, and consequently more expected yield. Okay. And if we take a look, just to review how we've done each of those, we're doing basically the same thing. We're taking the two tranches that we've already created. We're pulling all of the mortgages from those. So we're not calculating the values that are going into these CMOs from the values in the tranche themselves. We're actually going down to the underlying mortgage and all of that detail at the mortgage and customer level to create these new CMOs, right? So that's how we maintain the traceability. We can be clear about our risk. We know what's going into each one of these CMOs so that we can provide that information to our investors as well as to the regulators. And then if we take a look, here's our two CMOs. And if we expand those, so you can see here's the CMO. We can see the expected yield. This is the AA CMO. We can see the median risk, the maximum risk that's gone into this, as well as the average risk, the total value of all the mortgages that are in this loan. So it's quite high. We can then also see the relationships that sit off of that. And then the detail, of course, that's in each one of those tranches. So here's our AA tranche, our AAA and BBB, and then we can see in this particular interface the number of mortgages that we'll be able to see is much lower, but you can see that we can still follow that relationship all the way down from the CMO into the tranches, into the individual mortgages, and then of course from those mortgages all the way down to product level as well as the borrower level detail. So I think in real life, of course, there'll be a lot more data. This is still a pretty small data set, I think, and if this were to be done for a large international bank or a large international financial organization, they would have a lot of additional complexities. So there would be more geographies, more cities, more areas in which the mortgages would be placed. There could be currency complications. So you might have loans in different currencies. We could add payments in here. So we've shown late payments, but we could also show individual payments. And then, of course, you could use this not only to calculate the overall risk, but to calculate the cost of the individual tranches or of the CMOs, as well as to manage it going forward, right? So, as defaults happen, as risk levels change, you can keep all of that information up to date in real time, right, in the graph. So that's what we have today for the demo. And now we can go over to some Q&A.